In this section, we look at a number of elementary properties of the real numbers, which in more elementary courses are usually taken for granted. As we will see, however, these are all actually consequences of the least upper bound property of the real numbers. Theorem: if x and y are real numbers, and x is positive, then there exists a positive integer n such that n times x is greater than y. Let's try to illustrate this inequality with an example. Consider x as 2/7 and y as 5. Then we can find a positive integer n such that n times 2/7 would be larger than 5. For example, the number could be 70, because 70 times 2/7 is 20, which is surely larger than 5. Let's see the proof of the theorem. If y is negative or 0, then the statement is true for all n. Because in that case, the right-hand side is 0 or negative, then the statement is true for any n, because since x is a positive quantity, so the left-hand side is positive. Thus, we assume that y is positive. We will use the method of proof by contradiction. Let A be the set of all positive multiple of x. Namely, A is the set of all elements like nx, where n is a natural number. If the statement is false, that is, there does not exist any n such that nx is larger than y, then, since R is an ordered set, by the definition of an ordered set, nx must be either smaller or equal to y for all n. Thus, y is an upper bound of the set A. Since A is non-empty and R is complete, or the least upper bound property of R says that the supremum of A exists in R. Let the supremum of A is alpha. Since x is positive, so alpha minus x is smaller than alpha. Therefore, alpha minus x is not an upper bound of the set A. And thus there exists an element of A such that mx for some m, such that alpha minus x is smaller than mx. So we have an alpha here, we have some alpha minus here. So since any number smaller than alpha, by definition, cannot be an upper bound, since alpha is the least upper bound. So there must be some element mx of the set A. This is the inequality, which could be at most alpha. So taking the first inequality and transposing the x to the right-hand side of the inequality, we obtain alpha is smaller than the product m plus 1 times x. But the quantity m plus 1 times x is in A, because A contains any positive multiple of x. But this contradicts the fact that alpha is an upper bound of A, because we have a quantity which is an A is larger than alpha. So this contradicts the fact that alpha is an upper bound of A. Therefore, the original statement is true, since our hypothesis became wrong. This concludes the proof of the Archimedean property. Let's see another consequence of the least upper bound property of R. If x and y are real numbers with x smaller than y, then there exists a rational number R such that R is larger than x but smaller than y. It simply says that if we take two real numbers, x and y, with y larger than x, then there would be some rational number somewhere in between x and y. Let's see the proof of this theorem. Proof. We assume first that x is non-negative. Since y is larger than x by hypothesis, then y minus x would be positive. Then by the previous theorem, the Archimedean property, there exists a natural number n such that n times y minus x would be larger than 1. Here we are assuming that this is x and this is y. Or 1 plus nx is smaller than n, just by reorganizing the term of this inequality. Again, by the Archimedean property, there exists another natural number k such that k times 1 is larger than nx. Now we are assuming this quantity as y and this quantity as an x. Let A be the set of all positive integers L such that L is larger than nx. A is non-empty because k is there. K is in A because k is a positive natural number such that k is larger than nx. So k must be in A. So A is non-empty. So by the well-ordering principle, there exists a smallest positive integer m such that m is larger than nx. In other words, m minus 1 is smaller than or equal to nx, which is strictly smaller than m. Now taking this inequality here and this inequality here, we obtain two inequalities. Namely, the second inequality gives nx is smaller than m, and the first inequality gives m minus 1 is smaller or equal to nx. The second inequality can be written just by transposing the 1 to the right hand side as m is smaller or equal to 1 plus nx. But as the equation 1, we obtained that n plus nx plus 1, which is smaller than ny. So we have two inequalities now. Nx is smaller than m, and m is smaller than ny. Now dividing the inequalities by n, we obtain this expression. In the left hand side, we obtain x. In the middle, we obtain m by n. And in the right hand side, we obtain y. So this shows that between any two real numbers, x and y, there exists some number of the form m over n, where m and n are positive natural numbers. So it must be a rational number. This concludes the proof of the theorem. The figure illustrates the previous theorem. If we take any two real numbers, x and y, on the number line, then there would be some rational number in between, somewhere. This theorem is also known by the statement that rational numbers are dense in reals. It means between any two real numbers, there is some rational number. No matter how close we assume two real numbers are, there will be some rationals fitting in between them. It has a great consequences we will explore later.